April 22nd, 2025, Red Sea, 0217 hours. A guided missile destroyer is running darkened ship 19 miles north of the Bab el-Mandeb Strait, moving 12 knots into a wind that smells like diesel and salt and distant shore fires. The sea state is low, the horizon is a hard line, and the threat picture is the kind you can't see with your eyes. It lives down in the math of radar returns and the whisper of radio frequency energy. On the port bow, a contact pops at 38 nautical miles, low altitude, is slow speed, tiny radar cross-section. Another appears at 41, then 44. They're not jets, they're not missiles. They're cheap. They're drones, the kind that cost less than a Navy helicopter's fuel bill for a single hour. The kind an adversary can launch in stacks and swarms until your screens look like static. To analysts watching from shore, this looks like a gift. A $2.2 billion ship with a crew of roughly 330 sailors inside a narrow sea lane, predictable track, limited room to maneuver. If the drone operators imagine they've solved the puzzle, get close, saturate the defenses, force the Navy to burn million-dollar interceptors on $20,000 airframes, and eventually one gets through. They imagine proximity equals vulnerability. They imagine every mile the drone closes is 1 mile closer to the kill. But they're doing the wrong arithmetic. Not just a little wrong, catastrophically wrong. Because for the U.S. Navy, the most dangerous place for an enemy drone is not far away. Yet it's close. Up close, the drone loses its greatest advantages: ambiguity, horizon masking, and time. Up close, the drone enters a cage made of physics and sensors and doctrine, where the Navy stops reacting and starts harvesting. Today, we dissect why the Navy loves when enemy drones get closer, and why that closing distance you keep hearing about is often the moment the attacker has already lost. From the adversary's viewpoint, the logic feels airtight. A one-way attack unmanned aerial vehicle doesn't have to be exquisite. It just has to be numerous. It can be built with commercial components, a piston engine, a simple autopilot, and a warhead that doesn't need precision if it can get within a few meters of steel and antennas and deck equipment. The operator doesn't need a pilot with years of training. He needs a launch crew, a GPS coordinate, and a way to cue the drone toward a radar emitter, or a heat source, or a visual contrast over water. He can launch from beaches, from trucks, from improvised rails in a wadi. He can launch at night, at low altitude, in weather that forces manned aircraft to be cautious. And if he can get the drones close enough, he can force the Navy into a cost exchange nightmare. On paper, the paper looks brutal. A drone in the Shahed 136 class of threat or any similar one-way attack profile can be assembled for a fraction of the cost of the weapons used to kill it. Even if you don't pin an exact number on a specific model, the relationship is undeniable. The Defender's interceptors are precision manufactured, tested, stored, maintained, and integrated into a complex combat system. A single surface-to-air missile can cost hundreds of thousands to millions of dollars, depending on type and configuration. The attacker's drone is closer to a disposable aircraft. Cheap materials, minimal avionics, a one-time mission profile. From a purely economic view, the attacker wants to force the defender to spend gold on pebbles until the defender runs out of gold. Then there's geometry. The sea is wide, but radar is not magic. Low-flying targets hide behind the curvature of the Earth. A drone at a few hundred feet can be invisible to a ship's radar until it's closer than you intuitively expect, because the radar line of sight is limited by the horizon. If the drone is skimming at 200 feet, the ship might not see it until it is tens of miles away, not hundreds. The adversary reads that as a timing advantage. If the drone appears late, it compresses reaction time. If reaction time compresses, the defender is forced to choose faster, more expensive solutions. If the defender chooses expensive solutions, the attacker wins the economic game even if the drones die. Now add the historical texture that makes this threat feel real. Over the last decade, drones and loitering munitions have moved from novelty to mainstream. They've hit oil facilities, ships, airfields, armored vehicles. They've forced militaries to relearn lessons about air defense that were assumed solved after the Cold War. The adversary isn't guessing anymore. He's watched other conflicts. He's seen drones used as decoys to trigger radar emissions, to exhaust interceptors, to reveal positions. He's seen what happens when a defender relies on one layer instead of many. He believes the Navy, constrained by rules of engagement and identification requirements and the need to protect commercial traffic nearby, will hesitate. He believes the sea will amplify his saturation attack because everything funnels through predictable straits and shipping lanes. And he believes, perhaps most dangerously, that a ship is just a ship. A finite number of launchers, a finite number of missiles, finite crew endurance. He imagines a simple subtraction. If a destroyer carries a certain number of interceptors, and he can launch more drones than the ship can shoot down, then, by definition, something gets through. It feels like checkmate because it's framed as inventory versus inventory. So he builds his plan around range and numbers. He assumes he can launch from outside the ship's immediate awareness. He assumes the ship will see the drones late. He assumes the ship must fire expensive missiles early to avoid risk. But because letting drones get close is asking to die. Here is the pivot that changes the entire board. The Navy does not treat drones as tiny cruise missiles. The Navy treats them as sensors with engines attached, and engines are loud in every spectrum that matters when you have the right ears. The Navy treats them as communication problems first, aerodynamic objects second, and explosive threats last. The Navy also treats distance differently than civilian intuition. For civilians, distance is safety. For a modern combat system, distance is uncertainty. Far away is where false tracks live. Far away is where you can't classify quickly. Far away is where the target can hide in clutter, borrow the background, and force you into the most expensive shots. And the adversary's range math often ignores something the Navy is obsessed with: the difference between maximum range and effective range, between can reach and can kill. A drone that can theoretically fly 600 miles is not automatically a drone that can be guided, controlled, updated, and made lethal over that entire distance under electronic warfare pressure. A drone that can theoretically hit a point on a map is not automatically a drone that can do it while its GPS is being contested, while its control link is being hunted, while its navigation solution is being lied to. The adversary's analysts will highlight a map and say, "Our drone launches from this coast and flies this line to the ship." They'll draw a straight arrow and call it inevitability. But the Navy's fight is never drawn as a straight arrow. It's drawn as a volume of space where the ship's sensors and jammers and cooperative networks reshape reality. It's drawn as a kill web, not a duel. Do the math. If a low-flying drone is detected at 42 nautical miles and it cruises at 90 knots, that is 28 minutes to impact if nothing changes. 28 minutes sounds short until you understand what the Navy is doing inside those 28 minutes and what the drone is losing with every mile it closes. Every mile closer is a mile less time for the attacker to correct errors, a mile more signal attenuation for his control link, a mile more exposure to multiple sensors looking from different angles, a mile more chance that his drone's tiny mistakes accumulate into a miss, and a mile more time that the defender's system has to solve the classification and engagement problem with certainty. Because before the drone ever crosses into a range where the ship needs to shoot, before the operator can even enjoy that feeling of "we're getting close," the first hidden defensive layer has already been working for hours. The invisible war starts long before the visible one, and it starts with listening. Before the drone's camera sees the glint of steel, yes, the ship has already heard it. Before the drone's operator feels confident enough to lean forward toward his screen, the ship has already begun to map his fingerprints. Before the adversary launches his swarm, the Navy has likely been building a library of what those drones look like in the electromagnetic spectrum, what their data links smell like, what their navigation behavior looks like when they're healthy and when they're confused. On the destroyer's Combat Information Center, the room is lit like an aquarium. Screens throw blue and green onto faces that have learned to keep emotion out of their muscles. The first contact doesn't arrive as a dramatic blip with a siren. It arrives as a track file, and a track file is a hypothesis. The system assigns a number, a speed, a vector, an altitude estimate. But the ship is not waiting for the drone to become a thing. The ship is already reaching out with sensors that don't transmit at all. Passive detection is the secret opening move. It's how you fight without revealing you're fighting. The heart of that passive fight is electronic support measures, the part of electronic warfare that listens. When the ship's receivers collect radio frequency energy, they're not just hearing a signal, they're measuring frequency, pulse repetition, modulation, timing, angle of arrival. They're turning the enemy's emissions into geometry. Even if the drone itself is quiet, its support network is rarely silent. Somebody is talking, somebody is cueing, somebody is using a radar, a coastal surveillance system, a command post transmitter, a relay. The ship's sensors collect those whispers and stitch them into a picture that is often clearer than radar, because radar can be deceived by shape and flight profile, but a network's emissions reveal intention. Before the adversary's drone gets within a range where he thinks, now the ship has to react, the ship may already know which shoreline node is controlling the mission. It may already know which frequency band the control link prefers. It may already have a baseline of that link's normal pattern, which is crucial, because electronic warfare is not just noise. Modern electronic warfare is selective pressure. It is not about screaming louder. It is about touching the enemy's nervous system at exactly the point that makes him flinch. This isn't the old paradigm of jamming everything and hoping the target goes away. This is the new reality of precision electronic attack, where the defender chooses what the enemy is allowed to perceive. Aboard modern surface combatants, the electronic warfare suite is not a side tool. It's a weapon system, integrated into the combat system's decision-making loop. When you see references to the Surface Electronic Warfare Improvement Program, SEWIP, you're looking at a Navy effort to upgrade how ships sense and respond in contested electromagnetic environments. The point is not merely to jam drones. The point is to manipulate the entire chain that makes drones dangerous: detection, tracking, guidance, and terminal queuing. Consider the adversary's experience as the drones get closer. In his mind, closing distance should improve his control. He expects his link to strengthen, his video feed to sharpen, his latency to drop. He expects proximity to mean certainty. But the ship is waiting for that moment, because proximity also means the ship's countermeasures can operate with more discrimination and less collateral impact. And it means the ship can collect better signal characterization. The closer the drone gets, the more the ship can isolate it from other emitters. And the more confidently it can apply tailored effects without guessing. The adversary sees his drone at 30 nautical miles on his own situational display, perhaps derived from a coastal radar or from the drone's own telemetry. He feels the satisfaction of a plan working. Then, without warning, his telemetry begins to drift. His drone reports a heading that doesn't match what he commanded. The speed fluctuates. The altitude holds, but the track line on his map begins to wobble like a drunk line drawn by a shaky hand. He assumes wind. He assumes a cheap autopilot. He assumes his own system is glitching. He doesn't assume he's being lied to, because humans are not wired to suspect the laws of navigation themselves are being manipulated. That lie can take many forms. If the drone relies on satellite navigation, then its position is an estimate created by timing signals from space. The physics is brutal and elegant. The receiver measures the time delay of signals traveling at the speed of light, and from those delays it calculates where it must be. That means if you can change the timing information the receiver believes, you can change reality as far as the drone is concerned. GPS spoofing is not science fiction. It's a clock attack. It is an attack on time, and time is position. At long distances, spoofing is hard to do cleanly without affecting other receivers, but without broadcasting too widely, without risking interference. Up close, where the ship can focus energy and where the geometry is tight, spoofing becomes more practical. The ship can create a local bubble of false timing that fools the drone into thinking it is somewhere else. The drone then corrects toward a location that does not exist. It flies the map, but the map has been edited. Even when spoofing isn't the chosen tool, jamming the control link is often enough. Yet because many one-way attack drones are not truly autonomous in the way people imagine. They can be pre-programmed to fly a route, yes, but many attacks still depend on mid-course updates, queuing, or terminal confirmation from an operator or a sensor network. Remove that, and the drone becomes a blind projectile with no ability to adjust when the ship moves, when decoys appear, when weather pushes it off course. And the ship is always moving, even when it seems stationary on a map. At 12 knots, the ship covers a nautical mile every 5 minutes. Over 25 minutes, it shifts 5 miles. 5 miles is enormous when the drone's warhead needs to hit a specific part of a ship to achieve a specific effect. The adversary's operator watches his drone's link degrade. He increases power. He changes antenna direction. He tries a backup frequency. He switches to a relay. But he is fighting physics now, and not the physics of speed, the physics of signal-to-noise ratio. And every communications link is a competition between the desired signal and everything else. If the defender can raise the noise floor at the receiver or can inject a more believable false signal, the receiver will obey the wrong master. And this is where the paradox begins to show its teeth. The closer the drone gets, the more of the ship's soft kill options become viable, and the more likely the drone is to fail without the ship ever firing a missile. The Navy loves when enemy drones get closer, because closer is where the ship can be certain enough to apply the cheapest effects. Far away, you hesitate because you can't always classify. Far away, you may be forced to spend more because you don't have time to test hypotheses. Up close, classification becomes easier. The rules of engagement become clearer and soft kill becomes more reliable. This isn't a gun duel, this is an information duel, and distance is not merely range, it is clarity. Yet now imagine the adversary's perspective in the most dangerous moment. He believes he has achieved saturation. He believes multiple drones are closing from different bearings. He believes the ship is overwhelmed. But on the ship, the combat system is not looking at many drones. It is looking at track quality, correlation, behavior patterns, and engagement zones. It is fusing radar tracks, infrared cues, electronic support measures bearings, and off-board sensor data. Yet it is comparing what it sees now to what it saw 10 minutes ago. And it is learning. Each drone that gets closer gives the ship more data. More data means better classification. Better classification means earlier, cheaper engagement decisions. In older eras, electronic warfare at sea could be a blunt instrument. You jammed a band, you threw chaff, you hoped the missile went for the wrong thing. But modern naval defense is built around a layered architecture where soft kill and hard kill are not separate worlds. They're intertwined. The ship is constantly asking, can we make this threat miss without revealing more than we need to? Can we force it to waste itself? Can we turn it into a decoy for us, a beacon that reveals the network behind it? Because the drone is not only a weapon, it is also a signal that someone is watching. Somewhere, a command post is coordinating launches. And somewhere, a radar is queuing. Somewhere, a data link is transmitting. The closer the drone gets, the more those support nodes must work to keep it lethal, and the more they reveal themselves. The drone is a thread. The Navy loves when it comes closer because the Navy can follow the thread back to the hand holding it. This is where the invisible war becomes offensive. The first layer is not merely defense, it is shaping. It is deciding what the drone is allowed to be. If the drone is allowed to keep its navigation, its control link, and its targeting, it remains a meaningful threat. If those are denied, the drone becomes a floating object with an engine and a warhead that will splash into the sea with no drama. And the beauty of this layer is that it scales. The attacker can launch more drones, but more drones also means more emitters, more coordination, more opportunities for the defender to detect patterns and apply selective interference. Saturation can backfire in the electromagnetic domain because each added drone is another receiver to confuse and another transmitter to exploit. The adversary's operator sees something that feels impossible. Two drones that should be converging on a target begin to diverge. Their tracks separate. One climbs unexpectedly, as if searching. One begins a slow turn that was never commanded. He assumes mechanical failure. He assumes cheap components. He tells himself that's why drones are cheap, because some fail. But the failure rate climbs too fast. It becomes systematic. It begins to feel like the sea itself is rejecting his drones. He does not yet understand that the ship has been measuring his drone's behavior and then applying effects to maximize confusion. Not random jamming, not constant blasting, but timed interference that hits precisely when the drone's guidance algorithm is most vulnerable, such as during waypoint transitions, during altitude corrections, or during terminal homing initiation. Guidance systems, especially low-cost ones, rely on feedback loops. Feedback loops can be destabilized. If you introduce false data at the wrong moment, the system overcorrects, oscillates, and loses stability. The drone looks like it is making mistakes, but the mistakes are induced. And then, when the drone gets closer still, the ship gains another advantage that seems counterintuitive. It can finally afford to use its eyes. At long range, radar is king, but radar is also ambiguous. A small drone can look like a bird, a wave, a civilian craft's clutter. At close range, the ship can cue electro-optical and infrared sensors to visually classify. Once classified, the rules of engagement tighten into certainty. The command team stops arguing about what if it's civilian, because the sensor feed shows the airframe, the engine glow, the flight profile, the lack of transponder, the hostile behavior. That certainty matters because it unlocks the next layers without hesitation. So suppose the adversary's drone survives the invisible war. Suppose it's autonomous enough that jamming the link doesn't stop it. Suppose it's pre-programmed to fly a straight line and dive into the ship's side like a flying mine. Now the fight moves from the invisible to the visible. This is where people who don't understand naval air defense think closeness is danger. Because they imagine a drone suddenly appearing at 5 miles and the ship helpless. But the Navy does not rely on a single moment. It relies on layered envelopes that overlap like armor plates. If the drone gets closer, it enters more of those envelopes, and each envelope is an opportunity to kill it with a cheaper tool than the one outside. This isn't the old paradigm of shoot the biggest missile you have as soon as you see a threat. This is the new reality of economy of force, where the defender chooses the minimum effective kill mechanism and reserves expensive interceptors for threats that truly require them. At the outer edge, a ship can engage aerial threats with long-range missiles, but drones often do not justify that expense unless the situation demands it. A ship might choose to hold those weapons for faster, more complex threats like anti-ship cruise missiles. That means drones are frequently addressed with medium-range and short-range systems, and increasingly with directed energy or guns, depending on the ship's fit and the tactical context. As the drone closes, the air defense system's track quality improves. The radar has more returns, more updates per minute, better signal-to-noise. The fire control solution tightens. The ship's combat system, integrated with the rest of the strike group through data links, can receive additional track refinement from other platforms. Another ship's radar, an aircraft's sensor, even a helicopter's perspective. Cooperative engagement is not just a buzzword. It is how you remove the enemy's most powerful tool, which is uncertainty. From the adversary's viewpoint, this is maddening. He expects the ship to be blind low to the water, to struggle with clutter. Instead, his drone appears to be tracked with calm precision. He sees his drone's path predicted. He sees the ship adjust slightly, not in panic, but in geometry. The ship is not trying to run. It is trying to place the drone in the most favorable engagement sector, where its own systems have the best angles and the least interference from superstructure. Even the ship's turns are calculated in the language of firing arcs. If the ship decides the drone must die kinetically, it can choose a missile, but not always the million-dollar kind. It can choose interceptors designed for smaller, closer threats, whose costs are still substantial but are justified by the value of a ship and the lives aboard. This is where the adversary's cost narrative becomes emotionally persuasive but tactically shallow. Yes, a drone can be cheap. Yes, an interceptor can be expensive, but the defender is not trading money for money. The defender is trading money for time, safety, and operational freedom. A destroyer that stays alive keeps shipping lanes open, protects other assets, and maintains deterrence. Yet the cost of losing it is not just the ship's price tag. It is the strategic ripple that follows. Still, the Navy is obsessed with reducing that exchange ratio. That obsession is exactly why the Navy smiles, quietly, when drones press closer. Close drones can be killed by weapons whose cost per shot approaches trivial compared to missiles. Close drones can be killed by guns, by rapid-fire projectiles, by proximity-fused rounds, and by directed energy that costs roughly the price of diesel burned to generate the electricity. Close drones are inside the realm where the defender can win economically as well as tactically. Now picture the moment a drone crosses inside the range where the ship's point defenses become dominant. The drone is no longer a strategic problem. It becomes a physics problem with a countdown timer. The combat system calculates time to go. It predicts where the drone will be in 10 seconds, in 15. As it chooses an engagement sequence, soft kill attempts continue, decoys may deploy if needed, then hard kill layers activate in a prioritized ladder. The adversary's operator, if he still has any connection, watches his drone's final approach. He expects to see panic, missiles fired wildly, tracers, explosions. Instead, what he sees can be unnerving in its professionalism. The ship's responses are measured. The drone's feed may show the ship briefly, then flicker as the link degrades further. Then return to a view of sea as the drone's nose dips. He imagines impact. He imagines fire. And then the drone simply disappears. If the kill is delivered by a missile intercept, the physics is not Hollywood. There is no slow chase. There is no dramatic near miss. There is a closing velocity so high that matter behaves differently at the instant of contact. When two objects meet at several times the speed of sound, even the energy density at the impact point is sufficient to shred structures faster than the material can flex. The drone's airframe, likely built light to maximize range, does not explode so much as it is torn apart into fragments that decelerate violently in air, scattering, burning, and then splashing into the sea. If the intercept is close enough, the drone's warhead detonates harmlessly away from the ship, a flash and a puff, and then darkness again. But the Navy's favorite outcome is often less dramatic than a missile kill, because the favorite outcome is control. The favorite outcome is the drone dying confused, missing, and splashing without ever forcing the ship to reveal the full shape of its defenses. A drone that crashes into the water because its navigation was lied to is not just a dead drone. It is a psychological blow. It tells the adversary that even his cheap threats require a sophisticated environment to be lethal, and that the Navy controls that environment. Here is the deeper paradox. Enemy drones getting closer feels like danger because you imagine the distance shrinking, the time shrinking, the threat looming. But for the Navy, closer often means the threat has crossed thresholds where the defender's certainty rises faster than the threat's lethality. Closer means classification is certain. Closer means rules of engagement are clear. Closer means the ship can apply narrowly tailored electronic attack without ambiguity. Closer means the ship can choose cheaper kinetic options. Closer means the drone is within multiple overlapping engagement zones, and the probability of kill climbs steeply. The adversary's best chance is often not close. It is far, where it can hide, where it can force expensive shots, where it can exploit uncertainty. That is why the Navy loves when drones get closer, because when they get close, they stop being an idea and become a target, and targets can be solved. But suppose the adversary adapts. Suppose he learns that simple one-way drones are being confused. Suppose he upgrades. Suppose he sends drones that are not just dumb GPS followers, but coordinated, using terrain masking, flying low, perhaps using passive sensors to home on emissions. Suppose he pairs drones with other threats, like anti-ship cruise missiles or ballistic missiles, trying to create a layered attack that overwhelms layers with layers. Suppose he launches decoy drones to trigger radar and then follows with real weapons. The Navy expects that because the Navy has been watching the same conflicts and drawing the same lessons. And that is where layers 2 through 4 turn getting closer from a perceived advantage into a trap with teeth. Because if the drone survives the invisible war and enters the hard kill zone, it is now facing a system that is designed not around a single weapon, but around probability stacking. Each layer is a separate way to kill based on different physics, different sensors, and different failure modes. The drone can be lucky once. It can be lucky twice. But it cannot be lucky through an entire architecture unless the architecture is broken, and breaking the architecture requires more than cheap airframes. It requires suppressing sensors, defeating data links, blinding fire control, and maintaining coherent guidance under intense electromagnetic pressure. That is not cheap. That is not simple. That is nation-state complexity. A drone at 20 nautical miles is in the zone where the ship's medium-range interceptors can engage with high probability if needed. But the Navy's doctrine is not to waste. If the drone is alone, if it is slow, if it is clearly a drone, the ship may hold missiles and continue soft kill. If there are many drones, the ship may begin to allocate intercepts selectively, killing the most dangerous tracks and letting soft kill handle the rest. The idea is to avoid emptying launch cells on disposable threats while preserving the ability to kill high-end weapons. This is where the adversary's cost comparison often becomes his own trap. He wants the Navy to spend $1 million per kill. The Navy wants to spend pennies per effect. The Navy wants the drone close enough that it can be engaged by the cheapest effective layer. That is why you will hear sailors and air defenders talk about forcing the threat into the inner ring. The inner ring is not where you die. The inner ring is where you kill with certainty. And inside that ring, one of the most brutal, least romantic layers is simply metal and time. Rapid-fire guns, proximity-fused ammunition, and the physics of fragments. When a close-in weapon system engages, it is not aiming the way a human aims. It is computing a lead solution faster than reflex. It is predicting where the drone will be and placing a cloud of steel in that future space. If the drone flies into that cloud, it is shredded. A small airframe cannot absorb much damage. Lose a wing, the drone departs controlled flight. Lose control surfaces, it tumbles. Lose the engine, it becomes a glider for seconds before gravity wins. The point is not elegance. Yet the point is that cheap drones are fragile, and fragility is a vulnerability that grows as distance collapses. The adversary's operator might believe close means too late. He imagines the ship has no time, but the ship's systems are designed for compressed timelines. They were built to fight supersonic sea-skimming missiles that give you far less time than a prop-driven drone. Compared to a Mach 2 sea skimmer, a 90-knot drone is slow motion. That doesn't mean it's harmless. Swarms are real. But it means the engagement timeline is not as hopeless as outsiders assume, and it means the ship can sequence engagements rather than panic. Now, because this title is about why the Navy loves drones getting closer, we have to confront the ugly truth. There is a point where closer becomes genuinely dangerous. At very close range, debris can still strike the ship. A drone's warhead detonating near the hull can pepper antennas, shatter sensors, injure personnel topside. Saturation can still create gaps if the defender is forced to split attention across multiple bearings. The Navy is not arrogant about that. It respects the threat. It trains for it. But it doesn't fear the way civilians fear. It treats the close fight as manageable, because the close fight is where the Navy has the most tools. And the Navy has been steadily adding new tools precisely because of this drone era. The most important addition is not a new missile. It is the integration of sensors and shooters into a coherent system. The ship is not alone. Even a single destroyer is rarely a solitary duelist in modern operations. It is part of a formation, part of a network. That network changes everything because it extends the ship's senses beyond its own radar horizon. A low drone can hide behind curvature relative to a ship, but it cannot hide from an airborne sensor that looks down. That's why naval aviation is part of air defense, even when it isn't firing. An E-2D Advanced Hawkeye airborne early warning aircraft, if present in theater, can see low flyers far beyond a ship's horizon because it sits at altitude. The physics is simple. Raise the sensor, extend the line of sight. What a ship sees at 20 miles, an aircraft can see much farther. That means the drone's late pop-up trick becomes less effective against a networked force. And that network does something else. It makes getting closer a liability because the closer the drone is to one ship, the more ships can see it from different angles, and the easier it is to maintain a continuous track. Track continuity matters because weapons need a solution. If you lose the track in clutter, you hesitate. If multiple sensors maintain it, you don't. So when the adversary pushes drones closer, he may be pushing them into a zone where the Navy's composite picture is most coherent. He is feeding the system the data it needs. This isn't the old paradigm where each ship fights with its own eyes and its own hands. This is the new reality where the force fights as one organism, and closer simply means the organism's reflexes get sharper. The adversary's third-person analysts, the ones who will later write memos about what went wrong, will often describe the moment as unexpected defensive effectiveness. They will talk about U.S. electronic warfare, about layered defenses, about disciplined fire control. But what they will miss, unless they think like engineers, is that the Navy's love of close drones is not emotional. It's mathematical. It's the recognition that the attacker's cheapness is tied to brittleness, and brittleness is punished hardest at close range where the defender can apply precise, low-cost effects. If the drone that is far away is a question mark, the drone that is close is an answer. And now we can step into the next layer sequence, where the Navy stops merely denying guidance and begins physically erasing drones from the sky in ways that make close feel like a cliff edge rather than a finish line. Because the moment the drone crosses into the engagement ladder, every rung above it is already prepared, already cued, already assigned, already rehearsed. The adversary believes he is forcing the Navy to react. In reality, he is entering a pre-built funnel. Suppose the drone survives soft kill. Suppose it is now at 12 nautical miles, skimming at 300 feet, heading steady, no transponder, no response to warnings, classification solid. The ship's combat system has done what it must do. It has moved from doubt to decision. Now the question is not whether to act. The question is which physics to apply first. Yet if the ship chooses a missile intercept at this range, it is not doing so in panic. It is doing so because the geometry is favorable and the probability of kill is high. A medium-range interceptor does not need to fly far. It needs to fly fast and meet the drone at the correct point in space. The drone's closing speed is low, which simplifies the intercept problem. The missile's seeker can acquire with higher confidence. The engagement can be timed to ensure the drone dies far enough from the ship to minimize debris hazard. But if the ship wants to preserve missiles, if it anticipates multiple waves, it may prefer to let the drone get closer still, into the zone where point defense missiles and guns dominate. That sounds insane to outsiders. It feels like letting a threat approach your throat. But remember what closer unlocks. cheaper shots. And a point defense missile designed for close threats is still a sophisticated weapon, but its use is part of a cost strategy as much as a survival strategy. And even cheaper than that is gunfire. Now imagine the adversary's operator in the final minutes. He sees distance collapse, 10 miles, 8, 6. He expects to see the ship fill the drone's camera view. He expects to see the bright line of a deck. He expects impact. Instead, he sees a sudden bright flare in the sky. Yet not from his drone, but from something leaving the ship at impossible speed. His camera may not even capture it. The frame rate and compression are too limited. He hears nothing. Then the feed cuts, because the drone no longer exists as a coherent object. In the moments after, the sea looks empty again, and the ship continues on its track as if nothing happened. That calm continuation is part of the message. The ship is not merely surviving, it is maintaining mission. Yet a drone attack that fails to alter the ship's behavior is not just a tactical failure. It is a strategic failure because it does not achieve the attacker's goal of shaping U.S. decisions. But the adversary is stubborn and he tries to scale. He tries to send 10 drones, then 20, then 50. He tries to coordinate bearings so the ship must split defenses. He tries to force the ship to fire so much that its own decks become saturated with activity and its crew becomes exhausted. What he believes exhaustion is his ally. This is where the Navy's love of close becomes colder. Because in a swarm, the defender's biggest challenge is not killing a single drone. It is managing the engagement sequence so that every layer contributes without stepping on the others. And to manage, you need classification, track quality, and timing. All of those improve as the swarm gets closer and the tracks become more distinct, more separable, more predictable. Here, drones far away can merge into clutter. Drones close are individual problems with individual solutions, and each solution can be chosen to match the threat's value. A drone that is clearly a decoy can be jammed or ignored. A drone that carries a warhead can be killed. A drone that appears to be providing targeting for a follow-on missile can be prioritized. Close range gives you the fidelity to make those discriminations. Yet the adversary's operator may not realize that his own get-close strategy is also shortening his own window to adapt. If his drones are being spoofed or jammed, he has less time to diagnose. If his drones are being shot down, he has less time to observe what shot killed them. At long range, you can watch and learn. At close range, you are inside a blender. The feedback loop collapses. So the Navy's paradox is not that it enjoys danger. The paradox is that it enjoys the moment the attacker commits, because commitment removes ambiguity. A drone that is still far away can be many things. A drone that is close and non-compliant is, by behavior, declaring itself. The Navy loves that declaration because it legitimizes decisive action, and it allows the defender to act with confidence. And in a world where the hardest thing is often not firing, but knowing when you are justified to fire, that confidence is power. We're going to keep climbing the ladder now, layer by layer, and you're going to see why the Navy's defensive architecture turns closeness into an advantage. You're going to see why the drone that tries to be cheap ends up forcing itself into the most expensive mistake, entering a space where the defender can kill it in multiple ways at once, while extracting intelligence from every second of its approach. You're also going to see why the Navy's favorite drone is the one that comes close enough to be studied, mapped, and defeated repeatedly, because every failure teaches the system how to win faster next time. The adversary believes the ship is a target. The Navy treats the ship as bait inside a controlled volume, and the drone as a data package delivering itself to the defender's sensors. That is the hidden logic. The attacker thinks he is closing for impact, but he is actually closing for capture. Capture of his signatures, capture of his tactics, capture of his network, capture of the truth about his capabilities. And now the next step is the transition from soft kill dominance to the first of the hard kill layers that makes the word closer mean something different in naval warfare. Not nearer to success, but nearer to inevitability. because the closer a drone gets, the more the defender can apply raw physics with brutal efficiency. And when raw physics is applied correctly, cheap airframes do not get heroic endings. They get erased. That erasure begins with the mid-layer intercept logic, where the ship does not chase, but solves, and where the attacker's final approach becomes a geometry problem the defender has rehearsed 1,000 times, with the solution expressed in milliseconds. The drone is at 9 nautical miles now, and the ship has already assigned the engagement timeline, already cued the sensors, it already selected the effect, and the operator on shore is about to learn the first hard truth of modern naval combat. Closing distance doesn't always make you more dangerous. Sometimes it just makes you easier to kill. The combat system doesn't feel excitement when the range ticks down, and it doesn't feel fear when the track closes. It feels resolution. A drone at 9 nautical miles is no longer a hypothesis. It's a solved classification with a countdown. The moment it crosses that distance, the ship's defensive stack stops looking like options and starts looking like a conveyor belt, because every layer is built around one ruthless principle. If the previous layer fails, the next layer is already inside the threat's timeline. The adversary thinks he's compressing your reaction time. What he's actually doing is walking into your shortest, most practiced engagement loops. At 9 nautical miles, a small prop-driven drone flying 90 knots has roughly 6 minutes to impact. 6 minutes is an eternity compared to the threat's naval air defense was built to defeat. Supersonic sea-skimming cruise missiles can give you less than a minute from first detection to terminal maneuver. That's why, in the dim blue light of the Combat Information Center, no one is shouting. The watch team isn't improvising. They're executing. The ship's radar is updating the track, and the fire control solution is stabilizing, and the electronic warfare suite is still probing the drone's link like a scalpel probing a nerve. The drone, meanwhile, is losing the one advantage cheap systems rely on: a stable feedback loop. The closer it gets, the more the ship's countermeasures can isolate it, and isolation is how you kill without spending. But suppose the drone is autonomous and stubborn. Suppose it doesn't care that its control link is jammed. Suppose its inertial measurement unit keeps it pointed down a pre-programmed track line. Suppose it's flying a simple suicide geometry: straight line, constant speed, terminal dive. The adversary's operator has lost his live connection, but he doesn't need it. He only needs the drone to keep going. This is where Layer 2 starts, and Layer 2 is about something people misunderstand at sea. You don't have to see a drone to prepare to kill it. You only have to see the volume of air it must pass through. Naval air defense is built around engagement zones, and an engagement zone is not a circle on a map. It's a three-dimensional funnel defined by sensor coverage, weapons kinematics, and time. The drone is entering a funnel that has been engineered for decades, and what makes it lethal is not a single missile or a single gun. What makes it lethal is coordination. Out beyond the destroyer's own horizon, an airborne sensor may be painting the low-altitude picture from above, turning what would have been a last-minute surprise into a long, calm track file. In some operations, that sensor is an E2D, Advanced Hawkeye with its AN/APY9 radar, looking down at the sea and seeing low flyers earlier than any surface radar can, because altitude extends line of sight. In others, it's a patrol aircraft, a helicopter, another ship's radar from a different geometry, or even a fused feed from multiple sensors stitched into one shared picture. The point is that the destroyer is rarely blind and alone, and the drone is rarely as hidden as its operator thinks. When the Navy talks about cooperative engagement capability, CEC, that's not marketing. That's a way of turning separate platforms into one distributed sensor and shooter organism. One unit can see, another can shoot. One unit can provide precision track data. Another can launch the weapon that rides that data into the intercept. The adversary's analyst, sitting in a room far from the sea, imagines the destroyer as an isolated chess piece. He imagines a drone popping over the horizon and forcing a frantic close-in reaction. But in reality, the destroyer is plugged into a tactical picture where tracks are being correlated across the formation, and that correlation is what drains the drone of ambiguity. A track that might have been dismissed as clutter on a single radar becomes undeniable when three different sensors agree on speed, heading, and behavior. The closer the drone gets, the higher the track confidence becomes, and the faster the kill chain can move from monitor to engage. Here's where the Navy's love of proximity becomes almost cruel. The drone's operator wants closeness because he believes it increases his probability of hit. And the Navy wants closeness because it increases its probability of identification. And identification is what unlocks economical, scalable engagement. If the threat is far, you hesitate because you might be wrong. If the threat is close and still behaving like a weapon, you don't hesitate, and you don't need to spend your most expensive interceptors to be safe. Cost is the attacker's favorite story, so let's validate it honestly before we bury it. A low-cost one-way attack drone might cost, depending on design and supply chain, somewhere in the tens of thousands of dollars. The defender might respond with an interceptor that costs hundreds of thousands or more. That sounds like a losing trade until you compare it to what's being protected. A $2.2 billion ship and a crew whose lives cannot be bought back are not balanced against a drone's price tag. But the Navy still cares about the exchange ratio because wars are marathons, not duels. So Layer 2 is designed to give commanders choice. The ship does not have to fire the biggest missile in its inventory at every small track. It can assign the minimum effective force with the highest probability of kill. It can also let the drone come closer, specifically to unlock cheaper hard-kill methods. And this is where the drone's get-close instinct collides with the reality of naval point defense. The closer it gets, the more the defender can use weapons that are brutally efficient precisely because they're designed for the last seconds of life. But suppose the adversary is not sending one drone. Suppose he's sending 12, with staggered approach angles, trying to split the ship's fire. Suppose he's mixing in decoys with slightly different signatures. Suppose he's learned that simple drones get spoofed, so he's sending drones with better inertial navigation, better anti-jam antennas, perhaps even passive sensors that try to home on ship emissions. In his mind, this is escalation. In reality, it's confirmation. It's the moment he reveals that the drone is not just a cheap nuisance, it's an integrated part of a strike system. And when he reveals that, the Navy is allowed to treat it with higher lethality earlier, because now the drone is no longer maybe. It is behaviorally hostile. The Chinese operator in a coastal command post, watching a composite display of tracks, believes he is constructing a saturation puzzle. He watches the drones close from different bearings, and he imagines the destroyer's radar overwhelmed, its interceptors allocated incorrectly, its crew forced into mistake. He imagines a ship as a human organism that can be startled into freezing. But the ship is not one brain. It is a combat system built to prevent exactly that. Track management is automated. Threat evaluation is rule-based. Engagement doctrine is pre-planned. Humans supervise. But machines handle the geometry at the speed required. At 6 nautical miles, the drone is inside the zone where the ship's point defense timeline becomes decisive. The combat system calculates intercept points and engagement windows in seconds. If a short-range missile is used, it's not fired at the drone the way you throw a rock at a bird. It's fired into predicted space where the drone must exist if it continues on its vector. The missile's seeker takes over in terminal, and the drone dies away from the ship. But the Navy's favorite close solution when available is the one that flips the attacker's cost story on its head because it makes the exchange ratio not merely favorable, but humiliating. The attacker expects you to burn a missile. The attacker expects you to pay a fortune to kill something cheap. The Navy wants to kill a drone with electricity and time because the cost per shot of a directed energy weapon is measured in fuel and maintenance, and not in the price of a single-use missile. Now, the exact fit of directed energy systems varies by ship and modernization cycle, and the Navy doesn't pretend lasers are magic. Lasers have weather constraints, line-of-sight constraints, and power constraints. But when conditions cooperate, lasers deliver something the attacker cannot easily counter with more drones, because the limitation becomes not inventory of missiles, but heat management and dwell time. You are no longer running out of interceptors in vertical launch cells. You are managing power and engagement sequencing. Imagine the drone at 3 nautical miles, closing. The operator, if he still has any situational feed, thinks he's within striking distance. He thinks he's made it past the hardest part. And then the drone begins to fail in a way that doesn't look like a missile hit. There's no explosive flash. There's no sudden disappearance. Yet there's just a progressive collapse. The camera feed jitters, the nose dips, the drone begins an uncommanded roll, and then it spirals into the sea like a bird with a broken wing. If you were close enough to see it, you might catch a faint, bright point on the airframe, a spot of intense heat that moves with the drone for seconds. That spot is not a warning. It is the mechanism of death. Laser lethality is thermodynamics as execution. You are not shooting the drone the way you shoot a bullet. You are delivering energy to a specific area faster than the drone can shed it. You are raising temperature until materials change behavior. Polymer housings soften and deform. Composite structures delaminate. Adhesives fail. Control surfaces lose rigidity. Wiring insulation burns through. The drone's flight controller, a small computer that expects stable sensor inputs, begins to receive garbage because the sensors are heat damaged and the wiring is compromised. The autopilot tries to correct with control surfaces that no longer respond correctly. The feedback loop goes unstable. The drone departs controlled flight and falls. The kill looks almost anticlimactic, which is exactly why it is so strategically valuable. Anticlimax scales. Anticlimax is how you defeat swarms without emptying magazines. This isn't the old paradigm of one missile per target. This is the new reality of energy as ammunition. But suppose the adversary anticipates lasers. Suppose he tries to harden his drones with reflective coatings or rapid spins or by making them smaller, forcing less dwell time. Suppose he launches in weather, in haze, in dust, trying to degrade laser effectiveness. Suppose he forces the ship into the more traditional close-in defensive stack. Then, Layer 3 becomes the gun layer, and the gun layer is where the physics becomes violent in a way drones cannot survive. When people think of naval gunnery, they imagine World War II broadsides, yet big shells, slow rates of fire. Modern close-in defense is the opposite. It is high rate, high precision, short engagement windows. It is about putting a dense volume of metal into the air where the drone must fly. A close-in weapon system can fire thousands of rounds per minute, and that number matters because drones do not have to be hit like a target in a movie. They have to be made aerodynamically impossible. A drone's wing is a lever arm. A drone's control surfaces are small. Its engine is exposed, its fuel is limited. If fragments tear the wing structure, the drone doesn't limp forward. It stops being an aircraft, and when it stops being an aircraft, it stops being a threat. The adversary's operator might, in the final seconds, see tracer arcs in the night, not because the ship wants him to see, but because physics is indifferent to secrecy. He might see a sudden shower of sparks near the drone as rounds pass through. Then, he loses the feed because the drone's electronics are destroyed or because the drone itself is torn apart. Debris splashes into the sea. The ship's radar track drops. The combat system immediately searches for the next track because it never assumed this was the last one. Now, because your title is not How the Navy Shoots Down Drones, but why it loves them getting closer, we have to connect the lethality back to the paradox. These gun and laser layers are strongest at close range. Their engagement zone is not 50 nautical miles. It's measured in a few miles, sometimes less, because that's where tracking precision is highest and time of flight is negligible. If the drone stays far, it stays out of those layers. If it gets close, it enters the zone where the Navy can kill it with the lowest marginal cost, and that is exactly what the attacker didn't want. At this point, the adversary's cost trap has inverted. He wanted you to spend $1 million to kill a cheap drone. But at close range, you can kill it with gun rounds that cost comparatively little, or with directed energy whose cost per engagement can be dominated by electricity generation and system wear rather than a single-use weapon. That is a cost comparison the adversary never wants you to be able to make, because it makes his entire strategy of economic exhaustion collapse. He wanted to bleed you. Instead, he's bleeding himself, because each drone destroyed cheaply is one less drone in his inventory. At one less warhead, one less launch rail, one less operator hour, and you've lost nothing but fuel and time. Still, suppose he's not just trying to hit a ship with drones. Suppose he's using drones as part of a more sophisticated strike. Drones for reconnaissance and decoy, then a real anti-ship cruise missile sprinting in behind the confusion, or even a ballistic or hypersonic profile threat fired from deeper inland. This is where Layer 4 appears. And Layer 4 is the layer the adversary hates most, because it is the layer that turns his close drones into a beacon that guides the Navy to kill the bigger threat before it can matter. Layer 4 is the counterstrike and the networked trap, the realization that every drone that gets close enough to force you to react is also broadcasting information you can exploit. Where did it come from? What frequency did it use? What command node cued it? What radar guided it? What launch pattern does it reveal? Every one of those answers can be turned into targeting, and the closer the drone gets, the better your measurements. Better measurements mean you can strike the source. The adversary's operator sees his drone die and thinks the event ends there. He thinks he has simply lost an airframe. But the ship is not done. The ship has been collecting data the entire time: bearings to emitters, time difference of arrival, signal characteristics. Those data points can be fused with other sources, aircraft sensors, satellite cues, other ships' bearings, to build a location estimate. Even if it isn't precise enough for an immediate strike, it is precise enough to narrow the search volume. And once the search volume narrows, the Navy can do what it does best: allocate surveillance, refine, and then act. This is the part of the story the adversary often learns too late. A drone attack is not just an attack. It is also a way of revealing your infrastructure. The moment you launch, you expose patterns: vehicle movement, communications bursts, radar activations, command decisions. If you want your drones to be lethal, you usually have to coordinate. Coordination is communication. Communication is emission. Emission is detection. Detection is targeting. When the drone gets closer, the emissions required to sustain it tend to intensify. The command node might increase power, yet it might switch to a different band. It might activate a relay. Each escalation is a louder shout, and the ship is listening. That's why the Navy loves closed drones in a cold, professional sense, because closed drones tend to force their controllers to reveal themselves, and revealed controllers can be neutralized. Now, let's add the visceral, kinetic moment you demanded, the one that turns physics into drama, not through adjectives, but through phase change. Because the Navy's layered architecture is not only about stopping drones, it's about preventing the follow-on high-end weapon that drones are often meant to enable. Drones can be spotters. They can be decoys to trigger radar emissions. They can be part of a chain that ends in a high-speed anti-ship missile that does not give you 6 minutes, it gives you seconds. Suppose the adversary uses drones to cue a supersonic sea-skimming missile launched from the coast. Yet the drone swarm is not the spear. It's the flash of the hand before the punch. The ship's combat system has been treating the drones as one problem, while also watching for the moment the real punch appears. A different track, different speed, different altitude behavior. A missile track that accelerates rapidly, that skims low, that behaves like something designed to kill ships. And if that track appears, the ship's defensive posture changes instantly. Because now the engagement priority shifts to the highest lethality per second. The adversary's coastal crew lights the missile's booster. The missile tears forward. On paper, this is where the ship dies, because sea skimmers are built to minimize radar detection until late, and their speed compresses the timeline. On paper, the missile is a blade. The drones were the distraction to keep you looking elsewhere. But the drones getting close have done something else. They have forced the defender's sensors to be active and alert. They have forced the combat system into a high readiness posture. They have forced the ship's defensive operators into a mode where they are already cycling through engagements and not waking up from calm. The adversary thought he was creating fatigue. He was creating readiness. And then the intercept happens far enough away that the ship barely changes course. When a high-speed interceptor meets a high-speed threat, explosives are not the only kill mechanism. Sometimes the kill is velocity itself. A fragmenting warhead detonates near the target, sending a dense cloud of high-velocity metal into the missile's path. The closure speeds are so high that the relative energy is insane. The missile's skin is thin by necessity. It's an aerodynamic structure built to fly, not a tank. When fragments hit at those velocities, they don't politely punch holes. They create shock, spall, structural failure. They rupture fuel tanks. They shear control surfaces. The missile's guidance dies first, and then the missile dies second, because without guidance it cannot sustain a stable flight path at sea-skimming altitude. It impacts the water and disintegrates, its kinetic energy spent in a white explosion of spray and debris. But there is an even more brutal end when the intercept is closer to a direct collision at high speed, and a hit that approaches the logic of hit to kill. At combined speeds measured in multiple Mach numbers, metal does not behave like metal. It behaves like matter forced into a temporary state it was never meant to occupy. The moment of impact concentrates energy into such a small volume that temperature spikes beyond what structural materials can tolerate. The contact surfaces don't crumple, they flash. Solid becomes liquid, liquid becomes vapor, and vapor becomes plasma. A glowing, ionized gas that exists for an instant before it expands and cools. That is not poetry, that is thermodynamics. That is kinetic energy converted into heat so fast the material can't conduct it away. For a fraction of a second, the intercept point is a star in the atmosphere, and then it is gone, leaving only falling fragments and an empty patch of sky. This is not a threat. This is a physics demonstration. The adversary sees the blip vanish on his screen. He tells himself it must have hit. Yet he wants to believe the ship is on fire beyond the horizon. He wants to believe the drones did their job, but the ship remains alive because the drones coming close didn't overwhelm it. They fed it. They forced it into high readiness. They revealed the control nodes. They made the adversary commit. And commitment is what modern naval defense is designed to punish. Now we transition into the human layer because the machines and physics are only half the story. And your title's paradox ultimately rests on a moral logic that is uncomfortable, but precise. The question becomes, why does the Navy accept being inside threat envelopes at all? Why not stand off so far that no drone, no missile, no coastal battery can reach? Why take the risk of letting anything get close enough to fight in the first place? Because the Navy is not stationed at sea to be safe. It's stationed at sea to be useful. And usefulness is measured in minutes and miles and blood loss. Here's the part that makes the paradox real. A destroyer in the Red Sea or a carrier strike group in the Pacific is not there to prove it can survive. It's there to produce effects ashore and to protect people, Marines, soldiers, allies, civilians, commercial shipping, who do not have the luxury of standing off. If you stand off too far, you can't cover the lanes you're supposed to keep open. If you stand off too far, your aircraft spend their fuel just getting to the fight. What if you stand off too far, your response time becomes a statistic that kills people on the ground. Do the math. If your aircraft can cruise at roughly 450 knots, that's 7.5 nautical miles per minute. If you are 350 nautical miles away, that's roughly 47 minutes one way in ideal conditions, before you add launch preparation, tanking, routing, threats, and on-scene time. If you are 95 nautical miles away, that's roughly 13 minutes one way. Those numbers are not a convenience. They are the boundary between arriving in time and arriving to document a death. Now let's talk about why the Navy will accept risk to keep that time short. Because in modern war, the most unforgiving clock is not a missile flight time. It is the human body's failure timeline. A sailor topside takes shrapnel. A Marine ashore takes a round that severs an artery. A civilian in a struck merchant ship suffers blast trauma. The body doesn't negotiate. Massive hemorrhage has a predictable curve. Yet in severe arterial bleeding, minutes matter. There's a reason trauma medicine obsesses over the golden hour, and even that phrase can mislead because it sounds like a guideline. It's not. It's physiology. After severe blood loss, the cascade of shock, hypoxia, and organ failure accelerates. Early intervention saves. Delayed intervention becomes triage. A casualty with uncontrolled hemorrhage can die in minutes. If bleeding is somewhat controlled but internal, the window extends, but not generously. Survival rates drop sharply as time to surgery increases. The reason militaries build evacuation chains is because the chain is the only way to convert injury into survival. That chain is measured in fixed overhead plus travel time. You cannot reduce some overhead below a certain point. You must secure the casualty, manage airway, manage breathing, manage circulation, prepare transport, coordinate landing zones, deconflict airspace. Those tasks consume minutes no matter how heroic you are. So the only variable you can truly control is distance. And this is where the Navy's presence becomes a moral instrument disguised as steel. A ship close enough to launch helicopters quickly, to provide surgical capability, to serve as a node in a medical evacuation chain, is a ship that makes survival mathematically more likely. The Navy is willing to accept drone threats because the alternative is accepting casualties that might have lived. In the middle of that chain is a person you will never see on camera. And this is where the story stops being about hardware. In Section 5 of this logic, there is a 19-year-old from Ohio staring at a radar display at 0300, halfway through a watch, eyes dry, mouth tasting like burnt coffee, posture locked into discipline because fatigue makes mistakes feel comfortable. He's not thinking about geopolitics, he's thinking about track correlation, about not missing a low flyer in sea clutter, about the difference between a harmless contact and a weapon. He's thinking about a decision that might have to be made in seconds. He doesn't get to philosophize about whether the ship should be closer or farther. His job is to make the close position survivable, because that close position is what makes the Navy useful to people whose lives are on the clock. And that's the moral justification that makes the paradox make sense. The Navy doesn't accept risk because it enjoys danger. It accepts risk because distance is a currency, and the Navy is buying time with its own exposure. It is paying with steel so others can pay with survival. Now, if you're a taxpayer, the question becomes sharper. Why risk a multi-billion-dollar ship and hundreds or thousands of lives when drones and missiles exist? Why not keep the expensive assets out of range and operate with long-range missiles and satellites? Why not let machines do it from afar? Because the world doesn't work that way. Long-range strikes require targeting, and targeting requires persistent presence. Presence requires ships. Ships require proximity. Proximity is what makes your sensors relevant and your response time survivable. A satellite can show you an image, but it can't escort a merchant ship through a choke point. A long-range missile can strike a coordinate, but it can't loiter overhead to confirm a moving threat. A distant force can threaten, but it cannot reassure. The difference between deterrence and abandonment is often measured in whether the steel is visible on the horizon. And this is why the Navy chooses specific distances with the kind of precision that seems obsessive until you realize it is calculated against multiple clocks at once. aircraft sortie generation, fuel burn, radar horizon, missile engagement zones, medical evacuation timelines, and the time it takes a drone to go from detection to impact. Not 94 nautical miles, not 96 nautical miles, exactly 95 when the mission demands a balance between response time and survivability, and when the defensive architecture is positioned to make that range a trap for the attacker rather than a vulnerability for the defender. Not 19 miles, not 21 miles. Yet exactly 20 when the geometry of a strait and the coverage of an escort screen and the timing of air support create the highest probability of protecting what must be protected. Those numbers are not superstition. They are the intersection points where multiple systems physics overlap, which brings us to the architecture reveal, because the only way the Navy can love drones getting closer without committing suicide is if the close position is not a lonely one, as it must be an engineered posture. It must be a cage made of interlocking sensors, shooters, and links. If you remove one piece, the cage weakens. If you keep the pieces connected, the cage becomes something the attacker cannot escape. Pull back now and look at what's actually happening when a drone closes on a U.S. Navy ship and the ship appears calm. The visible ship is just the skin. The real system is the network around it. The destroyer is the node you can photograph. But its lethality and survivability are distributed. Its radar is one set of eyes. The electronic warfare suite is another. Its infrared sensors are another. Offboard, an aircraft extends the horizon, seeing low flyers earlier. Another ship's radar provides a different look angle, reducing clutter ambiguity. A helicopter can investigate contacts visually. A submarine, silent below, can monitor for surface launch patterns or provide its own intelligence, feeding the wider picture. Its satellites and national sensors contribute cues. All of it is fused into a common operational picture that is not static. It updates continuously, and it is shared. This isn't a single ship defending itself. This is a networked kill web defending a volume of ocean. Data links are the nervous system. Link 16 is one of the languages that lets aircraft, ships, and sometimes ground nodes share track data and messages rapidly. Cooperative Engagement Capability, CEC. It is the deeper integration that can allow one unit's sensor quality track to support another unit's weapon engagement. The point is that the shooter does not have to own the best sensor. The best sensor can be elsewhere, and the shooter can still kill. That matters against drones because drones exploit horizon and clutter. Airborne sensors defeat horizon. Multiple geometries defeat clutter. Networked correlation defeats deception. Now map the roles in plain terms. One platform serves as the forward listener, passively collecting emissions and building a fingerprint library of drone control links and coastal radars. Another platform serves as the long-range watcher, extending the radar horizon so low flyers cannot appear at the last second. The destroyer itself serves as the local execution node, holding both the soft kill tools to deny guidance and the hard kill tools to physically erase threats. Another ship, positioned to widen the defensive arc, adds additional interceptors and radar coverage, ensuring that a saturation from one bearing doesn't become a saturation of the whole formation. Air assets patrol to intercept, to identify, to provide early warning, and, if necessary, to strike the launch sites. And hidden beneath the surface is the piece that turns defense into deterrence. The knowledge that if you launch drones from a certain coastline, you are not only risking the drones, you are risking the infrastructure behind them. Because the Navy's response is not limited to swatting what comes inbound. The Navy's architecture is designed to trace, locate, and neutralize the source, whether through aircraft strikes, long-range fires, or other means authorized by the mission. The cage is not passive, it bites back. Remove the airborne early warning asset, and you shrink the horizon, making low flyers harder to see early. Remove the electronic warfare suite's effectiveness, and you lose soft kill, forcing you to spend more hard kill inventory. Remove the network links, and each ship becomes its own island, vulnerable to clutter and deception. Remove the layered point defenses, and the last seconds become a gamble. The architecture is not redundant by accident. It is redundant because redundancy is how you defeat saturation. But keep the architecture intact, keep the links flowing, keep the sensors fused, and now the adversary's core assumption collapses. He assumed closing distance would force you into expensive, panicked shots. Instead, closing distance forces his drones into your cheapest and most reliable engagement layers. He assumed more drones would overwhelm you. Instead, more drones give you more data, more signatures, more opportunities to identify and adapt. He assumed the ship would be blind low to the sea. Instead, your network extends vision above the curvature. He assumed the fight would be about inventory. Instead, the fight is about information, timing, and physics. This is why the Navy loves drones getting closer, because a drone far away is an uncertainty that can drain resources. A drone close is a certainty that can be killed efficiently, studied, and used to reveal the attacker's network. Up close, the drone is no longer the hunter, it's the specimen. And if you want the final hidden logic in one sentence, it's this. The U.S. Navy doesn't wait for drones to get close because it's reckless. It designs a battle space where the moment drones get close is the moment they become solvable at the lowest marginal cost, while simultaneously turning their approach into intelligence that tightens the cage for the next wave. The adversary's operator will still tell himself after the first failure that he simply needs more drones. He will tell himself that quantity is the answer. But quantity is only an answer when the defender is forced to pay the same price per kill forever. If the Navy's architecture exists to ensure the price per kill drops as the defender learns, while the attacker's cost rises as he is forced into more complex drones, more robust links, more hardened navigation, more training, more infrastructure. The attacker's cheap strategy becomes expensive the moment the defender can kill cheaply and trace effectively. And that's the architecture reveal. You're not watching a ship survive drones. You're watching a system harvest drones. You're watching a kill web convert proximity into advantage. You're watching physics and networks make a mockery of the intuitive belief that closer equals deadlier. So let's finish the paradox where it began. On that April 22nd, 2026 night in the Red Sea, 02:17 hours, with a contact that started as a small, low, stubborn return at 38 nautical miles and then multiplied into a pattern that looked, from the wrong angle, like inevitability. From shore, it looked like a $2.2 billion problem trapped in a narrow sea lane, moving 12 knots, unable to sprint away from a threat that could be launched cheap and often. From the drone operator's chair, it looked even cleaner, distance collapsing, time collapsing, the ship growing from a symbol into a shape, the final approach turning into a straight line that feels like fate. But fate is for people who don't understand systems. What actually happened out there is that every mile the drones closed didn't just reduce the ship's time. It reduced the attacker's options. Far away, the attacker can hide behind clutter, behind the curvature, behind ambiguity, behind the defender's rules and doubt. Far away, a defender has to spend attention and sometimes money just to answer the question, what is it? Up close, that question disappears, and with it disappears the attacker's greatest protection. Yet a drone that is close enough to be certain is close enough to be denied, close enough to be deceived, close enough to be shredded, close enough to be cooked, and close enough to be turned into evidence. The Navy doesn't romanticize that. The Navy engineers it. It builds a battle space where proximity is not a victory condition for the attacker, but a change of jurisdiction. The moment the attacker crosses into a zone governed by U.S. physics, U.S. sensors, U.S. doctrine, and U.S. decision speed. The reason enemy drones feel scary is because they're new to public imagination, and because they're cheap enough to be thrown away in numbers that look unnatural. But the sea has always been a place where cheap things die when they meet prepared metal. The only difference now is that the preparation includes invisibility, deception, and networks. Before the drone is close enough to be cinematic, it has already been processed. Its likely origin bounded by bearings, its link characterized, its navigation stressed, its track correlated across platforms. And then, only when the ship is certain, the ship chooses the cheapest tool that will end the problem without creating a bigger one. Sometimes that tool is an electronic lie that makes the drone miss the world. Sometimes it's a precisely timed burst of energy that turns guidance into nonsense and wings into soft plastic. Sometimes it's a cloud of metal that doesn't shoot the drone so much as deletes its ability to be an aircraft. And when higher-end weapons appear behind the drone distraction, the same architecture that calmly handled the swarm pivots instantly to the faster, deadlier geometry, because those layers were never separate. They were always meant to overlap. This isn't a ship trying to survive. This is a distributed nervous system trying to control a volume of ocean. And if you want the most uncomfortable, most honest reason the Navy accepts the risk of being close enough for drones to matter at all, it isn't pride, it's obligation. Those ships sit where they sit because distance is not merely safety. Distance is also delay, and delay kills. A ship that stands too far off might be perfectly safe and perfectly useless at the same time. The mission is not to be invulnerable. The mission is to be present, to be fast, to be a guarantee that when someone else's timeline collapses, when a merchant ship is threatened, when an ally calls, when a crisis turns minutes into a currency, you have the ability to spend those minutes before they're gone. Somewhere in that chain is the 19-year-old from Ohio in the Combat Information Center, eyes burning, hands steady, executing an engagement sequence that feels like sterile procedure precisely because emotion is the enemy of precision. He will never meet the people whose lives are protected by the fact that the ship can hold the line in the close fight. But the close fight is why he's there. So when you hear the phrase "enemy drones are getting closer," don't picture a countdown to catastrophe. Picture a funnel, picture a cage, picture the moment the attacker gives up his last advantage, uncertainty, and hands the defender the one thing the defender needs to win efficiently: certainty. The drone thinks closeness is pressure. The Navy treats closeness as clarity. The drone thinks closeness is bravery. The Navy treats closeness as math, physics, and discipline stitched into one decision loop. The drone thinks it's approaching a target. The Navy knows it's approaching an ecosystem built to make it fail, to learn from its failure, and to make the next wave fail faster. That's why the U.S. Navy loves when enemy drones get closer. Because in modern naval warfare, distance doesn't automatically mean danger, and proximity doesn't automatically mean vulnerability. Proximity means the engagement has entered the defender's most optimized zone, where the cheapest effects are most reliable, where identification is most certain, and where the attacker's entire cheap swarm theory can be inverted until the swarm becomes a donation of parts, signatures, and burned-out operator confidence. This isn't intimidation. This is geometry enforced by networked steel. If this changed the way you see the drone era, if you understand now why close can be the worst place an attacker can be, drop the word proximity in the comments. And tell me what threat you want dissected next. The line is measured. The cage is closed.